there's a powerful technique for proving infinitely many statements all at once that's called mathematical induction. So the idea is, if you have a collection of statements that you want to prove, and they all look alike, but the only thing that's different about them is some number that shows up in the statement, and we'll see an example in a second. So if you have these infinitely many statements, you can, one for every positive integer, you can prove them all true in the following way. First, prove that the first one is true, and then show that if any one of them is true, then the next one in the list is also true. And in that case, all of the statements have to be true. And the idea is, if you can prove S1 is true, well, we assumed that we were able to prove S1 is true, then S1 is true. Okay, good. But the second piece says that if S1 is true, then S2 has to be true, because S2 is, 2 is 1 plus 1. So if S1 is true, then this second statement proves that S2 is also true. Good, so now we have the second one in our list. But look, now we just showed that S2 is true, and our second statement here says that if one of them is true, the next one is true. Well, that means if S2 is true, then S3 has to be true. And then if F3 is true, S3 is true, then S4 is true, and so on. And you can see this proves all of the infinitely many statements with just a finite amount of work here. So this can be a really powerful technique because it gives you this extra assumption, right? Sometimes proving these statements individually would be quite difficult, but having this structure of all of these statements in a list, it lets us prove maybe the simplest one. Right? This is usually called the base case. Usually the base case is relatively easy to show. So it lets us prove just the simplest one, but then to form these links in the chain, we get this extra assumption. We're assuming that the previous one is true, and we're going to show the next one is true. And so having this extra assumption is what makes this whole thing easier to. It's what makes proving these infinitely many statements a finite amount of work. Okay, so just as an example, let's prove that if you add up some odd integers, you get a square. Okay, this expression right here, 2n plus 1, this is just my way of saying an odd integer, right? Because 2n, if n is an integer, 2n has to be even, and then adding 1 to an even number gives you an odd. Right? So here we're just adding up some odd integers. So notice that there's an n that shows up in this statement, and that's playing the role of the subscript here. So to show that S1 is true, we just need to plug in 1 for n into this statement. Well, actually, I'm going to plug in 0, not 1. So we're actually going to start with S sub 0, right? You can start with any number, right? This chain of implications will just start at whatever number you started at. So we're starting at 0. Okay, so let's show that this is true when n is 0. Well, when n is 0, what odd number is at the end of our list? If n is 0, this is just 1. Okay, well, and we aren't adding anything to it because our list starts with 1, ends with 1. There aren't any odd numbers between 1 and 1. So on the left-hand side, when n is 0, we just get 1. On the right-hand side, when n is 0, we get 1 squared. So their base case, when n is 0, we have to prove that 1 is equal to 1. Well, that's true, right? Nothing to prove there. Okay, so next we're going to show that if this statement is true for n, it's true for n plus 1. Okay, so assuming that it's true for n, that means that we are going to assume that 1 plus 3 plus and so on, all the way up to 2n plus 1, really is equal to n plus 1 squared. Okay, now we need to show that the statement is true for n plus 1. But what would that look like? Well, right, that's 1 plus 3 plus dot 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 up to 2n plus 1 plus the next odd. And the next odd is 2 times n plus 1 plus 1. Right? And then on the right-hand side, so we need to show that these are equal. On the right-hand side, when you plug in n plus 1, you get n plus 1 plus 1, so n plus 2. Okay. Well, on the left-hand, so we have to show that these two things are equal. But on the left-hand side, we have 1 plus 3 plus 5 all the way up to plus 2n plus 1. And our assumption was that that's equal to n plus 1 squared. Okay, now this bit here, this is 2n plus 3. Okay, which, so let's see, what could we do here? Let's multiply this out, I guess. So n squared plus 2n plus 1 plus 2n plus 3. Now we can combine like terms. So this is n squared plus 4n plus 1 plus 3 is 4. And look, that's n plus 2 squared, which is what we were hoping to get. So we did it, right? This shows that the sum of odd numbers is always equal to this perfect square, and it uses mathematical induction.